Hello, welcome to today's lesson. Today I want us to look at the theorem, the angle subtended by a diameter is a right angle. The angle subtended by a diameter is a right angle. Right, we're going to prove this theorem. We have a circle with a center, let's just say the center is O, and then we have a diameter, obviously AOB. Right, so we have our diameter AOB, and the diameter AOB is subtending an angle, let's say maybe it's angle C. Right, now the theorem states that the angle subtended by a diameter is a right angle. So we need to prove that angle C it's 90 degrees. It's a diameter. Now we simply say angle AOB it's twice angle C. This is the angle at the center theorem. The angle at the center theorem. Right, but then AOB is 180 degrees because this is a straight line. So it's a straight line, or we can even say it's a straight angle. So these are angles on a straight line. Therefore, we can conclude that 2C it's AOB, which we said is 180. And if we divide both sides by 2, we will get 90 degrees. Therefore, the angle subtended by a diameter is a right angle. Now, in this case, some people will say it is an angle in a semicircle. So when you give a reason, you can say an angle in a semicircle or an angle subtended by a diameter. So either ways, this angle therefore it's 90 degrees. The angle in a semicircle is 90 degrees. Okay, now I want us to look at other theorems which are also applying the angle at the center theorem. But for now, let's just look at this and practice this one and understand that whenever we see a diameter subtending an angle, we need to know that the angle is 90 degrees. But even if we see a circle and we see a chord subtending an angle of 90 degrees, then we must know that the chord, let's say AB, they say it's a chord subtending angle C, and angle C is 90 degrees. So if C equals to 90 degrees, then AB is not only a chord, but it is a diameter. So it means AB is not an ordinary chord, but it's a diameter. As long as the angle that it subtends is 90 degrees, then it means it's a diameter. So the diameter subtending a 90 degree angle, it's a chord. We are looking at the theorem. The angles subtended by the same arc are equal. In this case, we have arc AB, which is subtending the angles arc AB is subtending the angles ACB and angle ADB. So we are required to prove, we want to prove that these angles, it's angle C equals to angle D. Right, so construction, we join AO and OB. We join AO and OB. We want to have the angle at the center here. So we now have the angle at the center, so we can apply the angle at the center theorem. So we simply say angle AOB equals to 2 angle C. It's twice C. The reason is the angle at the center theorem is the angle at the center, angle at the center theorem. Right, now the same thing applies. Angle AOB again is twice angle D. If we look at AOB, is twice angle D. Same reason, angle at the center theorem. Now, you can see both AOB is twice C and AOB is twice D. Therefore, we can conclude that twice C is the same as twice D because they are both equals to AOB. So if we divide by 2 both sides, then we can say angle C equals to angle D. And then we have proved our theorem. So now let's look at the corollaries. So now what comes out of this theorem? We are looking at the following corollaries. Number 1, equal chords subtends equal angles at the center and at the circumference. Let's start with the circumference. So in other words, if we have a chord, maybe we have 2 chords, and the chord is subtending an angle, and we have another chord which subtends an angle, and the chords are equal. So if this chord equals to this chord, it means the angle that they subtend are equal. So if we have chord AB and chord CD, and AB is subtending angle E, while CD subtending angle F, and CD and AB are equal. So if AB equals to CD, then angle E, the angle they subtend, equals to angle F. So we say the reason is equal chords subtends equal angles at the circumference. So this may be in any way, so they can even cross the paths on their way. So one may be this way and the other may even go that way. As long as this chord equals to this chord, then this angle will be equals to that angle. So equal chords subtend equal angles at the circumference. Now, likewise, equal chords subtends equal angles at the center. Equal chords subtends equal angles at the center. So in other words, if I have a chord and it's subtending an angle at the center, and I have another chord and it's subtending an angle at the center, right? So if this chord equals to that chord, then this angle equals to that angle. If you look at these angles that are marked here, we can't say they are equal because they are vertically opposite. It's so clear here that these angles are not vertical opposite, but we are saying they're equal because they are subtended by the same by equal chords. So equal chords subtend equal angles at the center. So these are corollaries to this theorem, that the angles subtended by the same arc or chord are equal. So if they are subtended by the same arc or chord, it can even be a chord. So either it's an arc or it's a chord, so they are equal. So the corollaries here: equal chords subtend equal angles at the circumference of the circle, or equal chords subtend equal angles at the center of the circle. Thank you very much. Please don't forget to like, subscribe, and share. Thank you.